What's up, guys? Yeah, so welcome to my analytic number theory lecture. And previously, I discussed the property of the Dirichlet series, and today I'm going to do the Dirichlet series and the summation function. Okay, so what's going on? Okay, yeah, so I want to describe these two functions. So idea is that somebody gives you the arithmetic function, and you can form these two summation. One is the logarithmic, one is just the standard one. And our goal is to find a connection and also find a connection with the Dirichlet series. Okay, and hope you guys subscribe to my channel. Okay, so let me just talk about this famous results called the Mellin transformation. Okay, maybe in your undergraduate you heard about Fourier transformation and the However transformation and the Laplace transformation, but seldom people talk about Mellin transformation. I personally have some experiment about doing this kind of research, maybe 4 years ago or something. Okay, so this is the Dirichlet series, and such that it has a finite convergence of the epsinica. So this is called yeah, so basically what I'm saying is that after this sigma a, then this point, all these points are absolute convergence. Let's say somebody give you a Dirichlet series, and we need to find the relation between this m and l. Okay, so the theorem will tell me the first one is that f of s will be s 1 to infinity m f x minus s minus s minus 1 dx. Okay, so we just do a simple integration with x, and but with the powers minus s minus 1, and you plug s here, then you connect it to the Dirichlet series. Another is that this f of s is s minus 1 to infinity l f x minus s dx. Okay. Okay, so let's try to prove this. Okay, so let's start from, let's do a quick proof from 1 to 2. Okay, so I think 1 to 2 is very simple. Let's say you can just let s tilde to be let's say s minus 1, and you can define, let's say, right, you can define your f of tilde n to be f of n divided by n. Right, so if you do this, f tilde become f of n divided by n, and you plug it back, right? Now you can see that m of f tilde x will be l f of x. So if you plug this formula, let's say, let's maybe do this. Let's say you do f of s. Let's say you already proved the first one. Okay, let's say you already proved the first one. Now you can do what? You can in this case, right? So if you define f tilde n to be f of n divided by n, then what? Then your start from here, you get your f l f x will be just by definition, right? Will be m f tilde x, which is you use the first formula, which tell you that right. So right, you have this, and now you can now you have this, right? Okay, so if I plug in this, I should get f tilde s will be s 1 to infinity m f tilde x dx. So there's x minus s minus 1, x minus s minus 1. Okay, and so f tilde s will be s 1 to infinity l f x dx x minus s minus 1. Okay, so now final connection, just try to connect this f tilde s to originally fs. Okay, so this is just summation of fn and s, and this will be summation of fn and s plus 1, right? So all you need to do is just very simple. You can just plug this as f, I think it's f s plus 1, right? So which tell you that fs will be f tilde s minus 1. So now you have this, you get fs plus 1 equals to this. Then you just use this. So you get f of s equals to s minus 1, 1 to the infinity, L f x dx, x to minus s. Okay, so now we prove 1 implies 2. Hopefully the proof is simple. Okay, so it's very simple. You can try and implies 2. So we only need to prove 1. Okay. And I should give it a proof. Sorry, let me just quickly prove it. I think it's very obviously. Okay, so this is what our goal, right? And right, I think it's very easy, right? 1 to infinity, and then this is just summation of, let's say, f of n and less or equal to x dx, x minus s. Okay, then you can just try to do this integration with respect to x, and yeah, then you get an answer, right? Because this term will give you, or will give you f of n divided by n to s. Come from this integration. Okay. Yeah. So I think that's it. Okay. Maybe let's still give it a proof. Okay, proof. Okay. So let's write f of x as a, let's say let's define let's say chi of nx, f of n from 1 to infinity. Okay, so this chi of nx defined to be if n less or equal to x, I know 1, else is 0. Okay, so I can just take f1 to x and then m f of x. Let's call it x bar, x minus s. Okay, so this term can be written as s1 from x bar, summation chi xn, f of n. Sorry, this is nx. And then from 1 to infinity, by the way, this is chi. Okay, so this is s1 from chi bar, summation n less or equal to chi bar. Sorry, x bar, chi xn, f of n x minus s minus 1 dx. Sorry, my bad notation. This is nx. Okay, so now you do the integration, follow this step, right? So this guy is s f of n less or equal to x bar, 1 to x bar, chi nx, x minus x dx. So this part just directly computation. You just pull out this f of n, and then you do a simple calculation, right? This guy give you this. Okay, so you can simply check by yourself. This is f of n to the s. That's a chi bar. So x bar and x to s bar to s, m of f x. Okay, and then you just let x bar goes to infinity. So this type becomes this. Okay. Okay, so yeah, once we have this, let me just talk about a simple example that quickly describe analytic continuation. Analytic continuation of the zeta of the Riemann zeta of the zeta function. So I will talk about this Riemann zeta function in the future, and I will produce my own series about describe all the like the prime number theorem and Riemann hypothesis. Okay, but this video, let's just do a very simple thing. Let's say somebody give you a chi of s, just 1 under s. Okay, so this can be proved that the convergence, absolute convergence when real s greater to 1 using the P series. Now I want to extend it. So I want to extend to real s greater than 0. Okay, so one can use the following formula, which is this chi of s. Sorry, it's defined to be s minus 1, 1 minus s 1 to infinity. This bracket x minus s minus 1 dx. Okay, so x bracket is just x minus the floor of x. Okay, so you can check this is a subset. This is well defined when real s greater than 0. Okay, you can check these terms. Okay, hopefully it's obvious. Okay, except for s equals to 1. Okay, so we need to prove these two other set. Okay, at least when real s greater than 1. But for real s greater than 0, then so this formula is extended the previous one. Okay, so proof. Right, so we can use the Dirichlet series. Okay, so quickly, what we should do is that we do take m of fx, right? So let's say I for n to be 1. So this will be n less or equal to x, 1, right? So it's just the floor function of x. Okay, so now we're zeta s divided by s 1 to infinity. Use the previous formula, which is x minus s dx. Okay, so this is just the Mellin transformation, which we just proved. Okay, so now we just what we do what, right? So we just combine. We just write these terms. Right. So this is yeah, m of x. Yeah, right. So we just write. We can write x floor function x minus this, right? This is the definition. So x minus its fractional part will be the floor function. So we can just write zeta s, right? Then sorry, this is a bad notation. Zeta s to be s 1 to infinity, x minus fraction x minus x minus s minus 1 dx, and you can do your simple calculation. Get 1 s minus 1 to infinity, and the fraction of x minus 1 minus s minus 1 minus 1 dx. Okay, so this is first part. This is second part. Okay, so we prove. Yeah, so this is a standard standard Riemann continuation for real s greater than 0, right? If you just use this simple. Okay. And you can easily prove. I just say this. You can easily prove this is bounded by definition. You can try to prove it. It's not difficult. Okay, so let me just quickly say something. Okay, I want to say a zeta function. So I want to describe the zeta function when s approach to 1. Okay, so this is also a simple results that I think everybody knows about this. So this is, let me just write this. And so I know that when s equals to 1, there's a simple pole, and so this is the Laurent expansion when s approach to 1. Okay. Okay, so right, just write s minus 1 or s minus 1. So you can write the summation of a and s minus 1n. Okay, so let's say use. By the way, why this is true, right? So you can check this, and you know there is a singularity when s equals 1, and you know that it already be simple, right? Because you take out this part, and this part is finite in finite, right, in power of s. Okay, so that means I know there's simple here, and I can write this. So the remaining is to find this Euler Maseroni constant. Okay, hopefully it's not difficult. Okay, so by previously I can write this. Right, can I write this minus this? Oh, okay, so I can write this, and so this is 1 minus, let's say s, this. Okay, right, so this is just the previous result, and I want to compute this a0, right? So obviously what is a0? So a0 is just limit as s goes to 1. So a0 is the first constant, right? A0 is just s goes to 1. What is the left hand side, right? So what's the left hand side? Okay, so if you take this, obviously you can see this just take this, right? So we need to s approach to 1, right? So it's 1 minus 1 to infinity, the fractional part, x to the negative 2 dx. Okay, so we need to find this. Okay, and then you can check this. You can check this. So what is this? This is just the Euler-Mascheroni constant. Okay, so fact. 1 minus 1 to infinity, the fractional part x squared dx is the Euler-Mascheroni. Okay. Let me just finally quick prove this. I think this is not difficult. Let's say 1 to infinity fractional part dx. So from 1 to 2, you get 1 to 2, right? X squared dx. Let's say 2 to 3 dx. Sorry, the x. Sorry, I'm stupid. So, right, so this is the fractional part, right? So let's say from 1 to 2, you get x fractional part, right? So it's minus 1 x squared dx. And then you get 2 to 3 x minus 2 x squared dx. And, 3 to 4 x minus 3 x squared dx. And just keep going. Okay, so this is negative, right? So you can see that if you combine all the x terms, right, you get something like x squared x, and then you go 1 to infinity. So this term will blows up, right? But you don't need to worry because there's a minus sign for each term, right? So for these terms, you get what? Plus 1 over x 2 to 1, and plus 1 over x 2, 3 to 2, and 3 over x 4 3. Keep going, and then there's a 1 minus here. Okay, and I think finally you can get 1 plus a half plus a 1/3 plus 1/4, right, plus 1 over n minus log n as n goes to infinity. Okay, so this is, yeah, I think this is true, right? You can check this. Okay, so it gives you gamma. Okay, so yeah, this is just the main transformation of these two functions and its relation to analytic continuation. And in the next video, I want to talk about these two functions, the arrow bounds, and prove the Merton's theorem. And after that, we can go to the prime distribution. Bye bye.